Perfect. Thank you very much for the introduction. So, my name is Filip, and I will be presenting a work that was done together with Flashbots. For those who are not familiar with Flashbots, Flashbots is a company in the Web3 space that is actively working on MEV topics, where some of them actually relate and are closely related to the aspects of using privacy-enhancing technologies to mitigate some of the external activities that we don't want from MEV. And as a part of the work with them, we are looking into the aspects of so-called proof of cloud, where we try to close the gap between the T deployment strategies for both bare metal and cloud deployments and make sure that the threat model of the TEs itself is strengthened. Before I dive into the details, who of you have heard about TEs? It's like, nice. I wish every crowd would be like that. You know, I think it's a very TE dense crowd. And just for full context, also, here are my collaborators that contributed to the work that we already have published preliminary results a couple of months ago, and the final work was published a couple of weeks ago, so it should appear on a preprint very soon. Okay, so let's dive into the details. So, for those who are familiar with TEs themselves, there are certain trust assumptions that are not very much fitting some of the types of deployments, especially if you are trusting the provider of the operator of your infrastructure to actually not really provide any type of or physically temporary device, because as a part of the threat model of TEs, they just decided not to consider any type of specific physical security to the chip themselves. We can discuss later on why is it the case, but this is something for another talk. Just we can take it as it is. So if you later on look on the other side on what is the information we're actually getting about the attestation of the information that actually you are getting from the TE, it doesn't mention anything about the operator you are that is running your infrastructure itself, which means to actually a discrepancy that your confidential virtual machine can be running on malicious infrastructure and you are not really aware of that. Even though, of course, certain aspects of that should be protected, still you cannot fully trust that your provider is not running your confidential virtual machine in a basement where they can have access to the sensitive information coming out of the TE itself. There are discussed solutions, for example, something like PPID, like Protected Platform Identifier, that is available especially in the Intel context, that can provide you the information regarding the CPU IDs, but still that would mean that later on the provider itself should have a database where they store this information and you can get this information out of the way. And besides that, it also provides some limitations. So it means that each of the by providers here, for example, I mean cloud providers or others, have to provide and share this information. It might vary because of that across different providers, which can mean that it's very easy to migrate maybe from infrastructure to infrastructure, or actually as we currently see when we compare, for example, Microsoft, Azure, Google Cloud and others, they also actually provide slightly different offerings just to have a different edge in their offerings. And of course, it also means that there is limited visibility with respect to the same node on the same physical hardware would actually have the same PPID, which is good for some use cases. But of course, if you want to have a different type of assurances, maybe actually you want to have unique information that is specific to your confidential VM itself. And other part is that is the information about the bare metal deployments, which are a little bit out of the scope. We already discussed these parts in more detail in the paper that was published, as I was mentioning. A couple of months ago. It's rather like a short paper where you can just like see and we try to motivate the problem itself. And the setting we are in general operating is that you have your provider, which is the provider P on the right, which is the one that is actually running the hardware. Then you have the host manager. You can think of it that in case I have a bare metal in Google Cloud or other type of provider, they actually are running the physical hardware, but later on I get access to it as a bare metal machine where I can actually later on deploy my host operating system, my hypervisor, and do whatever I want. In case, for example, of a confidential virtual machine, the host manager and the hardware provider will be the same entity, but in case you consider bare metal deployments in cloud environment, they can be actually two separate entities. And then on top of it, you have the confidential virtual machine operator. It is basically the party that is responsible for running your confidential virtual machines. And then on the other side, you have someone who wants to verify and deploy their sensitive workloads in this confidential environment itself. And of course, if you consider applications such as MEV, but of course, we can also go beyond blockchain applications. If you look into AI, where you have very expensive model, where you have very expensive data that you want to protect, you want to make sure that actually the infrastructure is providing the guarantees you want it to provide. So In the broad term, I already briefly talked about it. We have two types of scenarios. So firstly, we have the confidential virtual machine. So this is something that is very much commonly used by people in cloud. You can just like basically run and deploy your virtual machine and get access to it. And second one would be the bare metal deployment in cloud. For that, I don't have the table now with me, but I can show it to you later and we can discuss it later. There are very few providers that actually are offering currently bare metal deployments with, for example, TE capabilities like Intel TDX or others. And in order for the aspects of the scenarios to work, you need to, of course, deploy the trusted domain float, but we want to strengthen this regular flow as people are used to by these additional guarantees of the data center execution assurance, or in a simple terms, proof of cloud. So we want to make sure that the user themselves do not have to get, do not need to get as much additional complication. So meaning that everything should be orchestrated from within the trust domain itself. So meaning that if I have a confidential virtual machine, I have access to all of the information. I just want to basically do the similar fashion as I want before. And the other part, we also are looking into actually two separate roots of trust. So one will be from the trusted execution environment itself, meaning, for example, the root of trust in that case will be from Intel, that is signing that this is the trusted chip from Intel that you're interacting with. And then the other root of trust will be from the TPM, where it's not about necessarily about the TPM guarantees. Of course, we care about the TPM guarantees itself, but it's rather about who is the issuer to the certificate that is stored inside of the TPM. So in this case, if for example, Google Cloud would have their TPM running on their bare metal server, they would have to be the one issuing the certificate to the public-private key pair that is stored inside of the TPM that is binding the TPM to the physical location itself. So that way you basically will end up with these two roots of trust, one from the TPM and second one from the TD itself. And combining these different two roots of trust, you will be getting one part for the data center execution assurance, meaning the TPM one, that only Google Cloud will be issuing certificates to their dedicated TPMs on the hardware. And then you will have the same flow as you are used to from the TD itself. So in case you are fine with trusting the TD, it doesn't necessarily mean that it's anything. But even if the TPM flow is compromised, you still have the basic TD guarantees as you are used to. And for the context of the upcoming slides, I'm only focusing on Intel TDX. We have dedicated reasons why we only do that, but with respect to what we actually need to have, the current AMD attestation flow and the information that are provided as a part of the attestation are not sufficient, and therefore we only focus on Intel TDX. Namely, it's about the part of the runtime measurement registers that are not available on AMD, in the AMD attestations themselves. Maybe I can skip this one, but depending on the crowd, like how familiar are you with TPMs? Have you worked with them in the past? Not so much, okay. So just briefly, many of current both client, especially client-based PCs, but also server-grade PCs are actually equipped with Trusted Platform Module. It's a hardware element that is available on the motherboard, and it's being commonly used in enterprise solutions, for example, for features like secure boot, key storage, and attestation. But the important fact about TPMs, they do not necessarily provide capabilities during the runtime execution during the runtime of the system, but are only available, for example, if you are using something like secure boot, that once you are booting your machine, it measures the boot sequence is correct. But in case during the runtime your PC gets compromised, basically TPM secure boot doesn't necessarily help you with that until maybe the next boot. But then it's possibly already too late because certain stuff already can be leaked. And this information that are part of the attestation coming out of TPM are part of the platform configuration registers, or in short PCRs, that are only extendable, not overwritten. So, and we can see roughly the information that are basically written here. So you have like your microcode, the BIOS, the information about the BIOS, the ROM, the boot, the master bootloader, and then also the operating system loader. And TLDR, basically what you are getting out of the TPM is that you know what type of kernel you are running, and you know what are the kernel modules as well. After it's booted, in case the user decides to do something else, you have a problem. That is the reason why I will be talking about on the next slide. We are also relying on the Intel TXT technology that will provide us additional guarantees beyond that. But this is coming on the upcoming slide. And just like a slight detour, I will be also sometimes talking about physical TPMs. That is like really a physical chip, but sometimes also in the context of confidential virtual machines, you also can rely on virtual TPMs, which are basically natively available in the confidential virtual machine, but their trust assumptions are different because from the name as we can hear, it's virtual. So they don't necessarily provide a hardware root of trust, but can only have software root of trust. So basically, you can think of it that the hypervisor is spinning a dedicated interface for you that is attached to the virtual machine. But of course, in case the hypervisor or the host operating system is malicious, it's not ideal. So we also have to look into the way on how to protect and ideally bind the physical TPM to the VTPM. And this is basically the part also where the TXT will be fitting into the picture. So I already hinted at it a couple of times. So Intel TXT, or in the full form Trusted Execution Technology, it's a bit of an older technology that has been around for some time. It's gained quite some popularity in specific environments, especially enterprise environments. And again, it's a hardware-based security feature. So basically, all my talk is like look into the set of tools that you have provided by the hardware and see how we can combine them together. And we are basically combining all of this additional stuff together. And unlike TD that is basically already available and the TEs that is basically available to your virtual machine, TXT is rather focusing on the host operating system. So basically what TXT gets you out of the box is before you actually boot your hypervisor, you are extending again the PCR values that are not only the 0 to 7 like for the TPM, you're extending your TXT values in a secure fashion all the way until PCR values 22. You don't have to necessarily care about the numbers as much, just you can think of it that you can actually later on get a confidence that the hypervisor that is being run on your system is of a certain type. And it provides, because of that, also additional information and trust assumptions to the confidential virtual machine that can be running on top of it as well. And lastly, just like for the completeness, we have the Intel TDX, where we have either the bare metal deployment or also the parallel virtualization flow for completeness. So again, you're getting the hardware-based security features that are, in this case, provided to your confidential virtual machine. And the reason why we are also differentiating between bare metal and parallel virtualization is that, for example, Google Cloud is more offering the aspect of the bare metal deployments themselves, whereas parallel virtualization is available by Microsoft Azure, where the reason for the parallel virtualization is actually for usability of the system. So in case you, for example, want to perform live migration as you are used to from your virtual machine, and in the context of confidential virtual machine, you basically need this parallel virtualization that will enable your confidential VM to be moved from one physical platform to another physical platform during the runtime as well. And for that, for example, Microsoft Azure is implementing this solution based on the VTL0 or VMPL, depending if it's Intel or AMD, into the picture as well. Irrespective of that, our solution or our architecture called DCA should be applicable to both of these as well. And very important part of why people are using TEs besides confidentiality and integrity is, of course, the aspect of attestation, where you want to provide and prove to others as a part of the TD code that this is the particular binary, the particular code that actually I'm running inside of it, and I can prove it to others that my execution has happened inside of the TE itself. So looking into Intel TDX, as a part of the root of trust, we have Intel in the mix, which is happening at multiple flows. Either it's, for example, the fact that it's relying on Intel SGX under the host on the host operating system, but it's also the fact that some of the private keys that are actually part of the physical chip are also partially available to Intel, and there is some form of integration or interaction with Intel that you have to do once to register your platform, later on to be using the machine during the runtime without any issues. But once you have it set up, which is something that can be done, you basically are getting, as many times as you want, the full certificate chain that is identifying your unique machine, and you can also get the information about what is the parts that are part of the confidential virtual machine, so you can get information about the firmware, the drivers, the guest kernel that is running there, and also the aspects about the specific workload, which is especially happening in the runtime measurement registers, the RTMRs 2 and 3, that are providing you the information about the binary, but also ideally the workload itself. This is something that is differing between the different implementations, but and the different providers, but it's something that you don't have to dive into the details themselves. So the general idea, as I was mentioning, we want to combine these different roots of trust, one from the TPM, one from the TD, to make sure that we are getting our trust assumptions as we have from the TD, but we strengthen it by getting additional confidence that the provider we choose to trust is actually fairly operating our infrastructure itself. And the way how we do it, in a nutshell, is that we are building up the root of trust important here, just like to make sure, we are focusing both on confidential virtual machines and bare metal deployments as well. So this is something just to make clear that especially bare metal deployments are very attractive for us in the cloud setting, because then you have much more control over what is actually happening under the hood. Because I think in a recent paper that was released, I think by someone in the audience, we have found out that the trusted compute base of the confidential virtual machines that are provided by major providers is not the greatest. So that is the part why especially bare metals are a very attractive way to interact and deploy your solutions in the wild. And the way how we do it, we basically are building up our root of trust all the way from the physical platform of the TPMs using TXTs. Then we deploy a VTPM once we basically boot up the host operating system properly. And what we are getting from the VTPM is, again, same as we do for the physical TPM, we are getting the PCR values, but this time not for the physical host operating system, but for the virtual host operating system. And then later we can bind the information that are part of the T attestation and the VTPM attestation themselves, since the fact that the information that are part of either the RTMRs or the PCRs are overlapping in certain stuff. And through this, you basically get this binding of these two stuff together. Here is the stuff just like for interest. You can later on look it up. That are some of the information that actually are overlapping. So especially what is interesting for us is the RTMR 0 and 1, which is common and it's available by pretty much every provider. They can be mapped to the PCR values of 1 and 7 and 2 to 5 for the respective information. And then, of course, what is a bit tricky are the PCR values above, because they are mainly focusing on the OS application layer. But irrespectively of that, for us, the most crucial ones are the PCR values 0 to 7, which will be providing strong enough binding for us moving forward. And specifically due to that, just to again make the point that we don't want to discriminate AMD just for the sake, but because we have certain requirements that are not fulfilled by AMD, AMD just unfortunately doesn't provide the RTMR equivalent capabilities as they are. Okay, so just taking this information of these two different roots of trust, how do we apply it to the two different scenarios? First scenario, confidential virtual machines plus VTPM. Here, just to also make sure that the color coding has some meaning, meaning that the green is usually something that what we choose to trust. Meaning, for example, if I'm deploying my confidential virtual machine, I trust the stuff that is happening there. And then the orange one is the part that is maybe a little bit outside of our TCB. But irrespectively, especially if it's like in this gradient, we still have some form of trust, like in the context of what is happening under the hood. Because, for example, still the hypervisor can behave maliciously in the context of confidential virtual machine. There were a couple of recent attacks. We still, for example, want to make sure that there is, by default at least, availability provided to our system, because if the host operating system or hypervisor decides to cut us off, just we will lose access to our confidential virtual machine. But just looking at it from the perspective of the combination of the VTPMs, what just basically is an additional requirement on the side of the provider. They have to bind during the time of the lunchtime of your respective TD. They have to provide the VTPM capabilities to your TD. So that way, when you are running your load as you are used to from within the confidential virtual machine, you will be getting the TD quote, and you will be also getting the VTPM quote from within the CVM itself. And since the virtual TPM keys are being issued by the cloud provider, you will actually see also the certificate chain, for example, coming from Google Cloud itself. And then just like for you to get this information into the picture. So I'm not sure how I'm doing on time, but I think should be roughly okay. So we can a little bit dive into the details, how it looks like. So you want to deploy your, perfect. You, as a verifier, want to make sure that your workload is running in an environment that you are happy with. You basically take it, you deploy it into your guest trust domain, and then from within the TD, you are just like following the typical flow as you are used to request all of the information about the TD itself. There is a lot of abbreviations I don't have to go through, but just you get the idea. And you can also do the same steps for the VTPM. Just this time it's a bit easier. You just basically ask the VTPM, give me the quote that you are aware of. It will provide it to you, and you can just like do the combination of both of these in here. And you just provide either as a proof. You can think of it like there are also optimizations for privacy reasons or for succinctness. You can do some zero-knowledge proof from within the TD that this is a trusted platform that is running on, for example, respective Google Cloud deployment or others. For the bare metal, it becomes a bit more interesting due to the fact that actually we don't want to necessarily trust the underlying information because we can have an access to it. And especially, it can be, as I was mentioning, two different parties running the stuff, right? At this point, unlike with the confidential virtual machine that anyway, Google Cloud is running the stuff, I also trust them for the hypervisor and others. It's maybe okay. But for the bare metal, you can have still OVH or other type of providers running the infrastructure. Then someone else can come and deploy the host operating system, the hypervisor that maybe can be actually more malicious, right? And then they can even say, okay, I'm running the VTPM or whatnot, but later on you are running the confidential virtual machine on top of it. So for that, actually, you have a bit more considerations because the attack space or the attack vector and the trust assumption that you have, of course, is a bit more severe because the host operating system hypervisor can be a bit more malicious, even though if they're running actually in the right environment. So a naive approach would be just like, okay, I as a verifier, get all of the information as I was pointing out before. But of course, this is something that is not fully ideal because the underlying host operating system can be proxying all of the requests to a different platform. So you can think of it, we call it Frankenstein attestation. But basically, you have an attacker that is running part of the compute on an trusted infrastructure, for example, like Google Cloud. They actually spend the effort and deploy the stuff in Google Cloud. They are able to access the information from the physical TPM that is having the right key material, and they are actually running other part of the workload. In this case, they will be basically running the confidential virtual machine in their laboratory where they can actually get access to the information. And they basically are trying to fool you that, okay, the TE itself actually is being compromised and it's running in my laboratory where I'm having all of the nice gadgets to get the sensitive information out, but I'm also giving you the attestation that looks like actually I'm running my stuff in Google Cloud. So this is basically the main idea of the Frankenstein proxy, where we want to make sure that the possibly malicious host operating system and the host stack cannot actually very easily do it. And this is the part where TXT come into play. Because with using the aspect of the Intel Trusted Execution technology, you actually get more confidence about the part of the hypervisor, the host operating system, because you are getting also additional runtime information that are provided to you by default. And you can actually also, in addition to that, you can, even though you are running the VTPM out of the hypervisor, you can actually make sure that also the keys that are being used for the VTPM are, for example, sealed against the PCR values that are only unlocked to you if you behave according to the expectation itself. Yeah, so the other part that is actually important, by using TXT, we actually also get the other feature that is very important for us, which is that we are able to bind the physical TPM to the virtual TPM itself as well. So basically, what is the only stuff that the provider has to do? They just have to set up a typical public key infrastructure to issue a certificate for the respective endorsement key that is stored on the physical TPM. And later on, if you just deploy the components as I was mentioning afterwards, basically this is it. This is something quite interesting because then the providers do not necessarily have to do anything else. They just basically, by issuing the certificate, which is just public key infrastructure, it shouldn't be as challenging. They should be able to provide you these capabilities. And the rest is on you as the operator, because all of the other parts are, I would say, some of them are a bit tricky, especially the Intel TXT is a bit of an archaic technology that is a little bit lacking documentation, but this is something that I guess for some of the researchers in the audience, we are used to a lack of documentation, and we have to go through certain pains and hoops to make sure stuff are working. But this is something that basically is later on providing the capabilities that you can do. And the other interesting and relevant parts is, which is not something against providers, if you look at the confidential virtual machine deployments for under the hood, they should do a lot of optimizations for you, and therefore they don't want to disclose it by default. So for example, the hypervisors are very much optimized for particular performance reasons, the same holds for the host operating systems, and they don't want to really open source it, which of course makes later on using such type of technologies where you will be getting confidence in the attestation will be lower because they don't want to disclose ever their source code of their applications. Whereas if you go with the bare metal deployments, you use commodity off-the-shelf software artifacts like hypervisors that are open sourced, hosted operating systems that are open sourced, you actually can get verifiability of all of the individual components along the way as well, which is quite neat. Yep, and I actually talked about this already. So in summary, with our approach, we are showcasing data center execution assurance, in short DCA, or also as we sometimes call it, proof of cloud, which is able and is supposed to be functioning for both confidential virtual machines and bare metal, just of course with different type of attack considerations that are covered in detail in the paper that should appear soon. And the way how we achieve it is by combining two separate root of trust, one from the TPM, one from the TD. And the main requirement here is basically just the certified trusted party. For example, Google Cloud is the one that is actually issuing a certificate to their endorsement keys on their physical platforms themselves. And overall, important message, we are strengthening the threat model of the current TDs. There is no dependency in case the TPM is compromised. Still, you can fall back to the traditional TD trust model that you are comfortable with. So this is just something to mention, that you don't have to use the additional capabilities. And we also argue quite extensively in the paper that even if the provider chooses to be malicious, for example, by not providing the VTPM or not providing you the endorsement key or the attestation or other stuff that they could do, they can actually be caught by doing it because you can still verify many of this information by yourself from running it from inside of the TD. So in the future work, we are also looking into some aspects of the privacy. So for example, if you look currently at the VTPM quote certificate chain, is actually providing way too many information about where actually your machine runs. So it's, for example, providing the information about the zone and the region where your cloud machine is running, which of course, depending on the application, it can be quite sensitive, especially if you consider aspects like MEV, that if you know where a particular builder is running, of course you can try to collocate. So this is something that you have to also keep in mind. And the paper will be available soon. I'm open to feedback, so if there is someone interested, just let me know. Happy to share and discuss further. And if we believe in the soundness of the threat model for the VTPM, we can actually also use the VTPMs for other type of considerations as well, which can be for dedicated key material storage, which can be later maybe more persistent. It can also be used ideally for some aspects of replay attacks and others, because this type of information can be later on unlocking quite new capabilities. And we hope to demo it so soon out there in the wild. So thank you for that, and I'm happy to take any questions from your side.